Forgot. Okay. Thank you everyone for joining us for our first NASA expert talk for the Artemis Roads 2 Challenge on Valentine's Day. Thank you for spending your Valentine's Day with us. We are really excited to welcome Dr. Caitlin Ahrens as our first NASA expert speaker. She's going to speak with us for about 30 minutes, and then we're going to open up the floor for questions. We've got some pre-submitted questions that we'll ask, but we'll also take questions live. So you can ask them in the video or you can put them in the chat. If you have questions during the talk, you can throw them in the chat. We'll try to keep track of them. Caitlin has a BS in both physics and geology from West Virginia University, and she's got a PhD in planetary science from the University of Arkansas. She's worked on a lot of different science topics. I'm actually kind of jealous, but a lot of work studying ices, including in the shadowed regions of the moon. So you guys have been thinking about that, but also on Pluto and other icy moons in the solar system like Titan and Enceladus. She's also thought about volcanoes in the solar system, including on Mars, Ceres, and Titan. And she has a long background of doing STEM outreach. So that's why we're really thankful to have her with us today. Currently, she's at the University of Maryland, College Park, doing a postdoctoral, which is what you do after you graduate from graduate school, fellowship at the Goddard Space Flight Center. So Goddard is one of the NASA centers. That's where they test all of the spacecraft before sending them out to space. And she's working as a technical research assistant for the Extravehicular and Human Activity Program for Artemis. So she's also thinking now about how to send people back to the moon. Okay, so I'm going to throw it to Caitlin, and she's got, like I said, a short presentation, and then we will open it up for questions. Okay.
All right. Thank you so much for having me here this evening. Super excited to talk about the moon because, yay, we're finally going back to the moon. It's going to be exciting, but my goodness, there are so many exciting challenges. So all of you guys have just prime opportunities to think about all the different things that we still need to work through. And this is not just my generation working on this. This is all of your guys' generation to help us out in the future as well. So we're gonna, well, or my PowerPoint is maybe not gonna work. Oh, there we go. Uh, so yes, what part of my introduction was, I've done a lot with different kinds of space systems. So I used to be a radio astronomer and like listening into space, doing earthquakes. I've done high altitude rocket payloads too. Mars was the first planet I got to work on, and then immediately tumbled into Pluto, working with the New Horizons mission. And now I do moon. Now I do lunar stuff. And with the moon is just keeping me busy from there on out. But a little bit about planetary science. What does a planetary scientist really do? And do I just have a geology degree? What about physics and so on? Planetary science is all sorts of different stuff. It's chemistry, it's biology, it's engineering, it's physics, it's geology, and all of these have different subdisciplines too. So biology could be not just how do we grow things on the surface of the moon or Mars, but then feeding our astronauts, what kind of food would our astronauts want to eat, whether on the surface of the moon or traveling back and forth, that would be in the realm of biology. Engineering, we want to uh, collect rocks and collect ice, which I'll talk about here in a bit. How do we do that? So that would combine engineering and the physics and the geology, maybe a bit of the chemistry. What kind of chemicals are we finding on the moon that we want to convert over to rocket fuel at some point? So, how do we be resourceful? How do we recycle all of these different kinds of minerals and materials and chemistry on the moon too, and make sure that we don't just dump and junk up the moon either? How do we recycle some of this? So, all of this is still very, very new, very exciting. So what all different aspects can we do with this though? It's not all about just sending rovers to a planet. It's not all about just sending an orbiter and take pretty pictures. That's very important for us. It's about getting that data. But then we have models as well. How do we model to better improve upon that mission data? How do we improve upon our models to go like, you know what? Maybe we should go to this part of the moon instead. Well, now we can go to the lab and build that. And does it work with the model, or maybe it doesn't? Maybe everything will crash, or maybe that lab work can help be like, oh, you know what? We didn't think about this. Let's send another mission to the moon or another mission to Mars because the models say one thing and the laboratory work maybe says something else. Let's send another mission. All of these kind of talk together, and all of these different ideas start interweaving with each other. So whether you're wanting to do more computer work, whether you want to be in a lab, or you want to build a mission, you want to send something out there. And all of these are very, very important for studying the moon in this case. But any planet, any solar system body out there would need those three main things here. So looking at the moon, it's beautiful. We've been to the moon several times. Here's our different Apollo landings back in the 60s and 70s. But notice that it's all kind of in the very dark regions of the moon here, and typically on just the one side of the moon. And that's not where we're going with Artemis. We're wanting to go to the pole. So Artemis 2 is going to be the first crewed test flight to the moon. It's going to swing around and land back to Earth. So it's not going to actually land on the surface of the moon. That's not until Artemis 3. So Artemis 2 is going to be a nice dress rehearsal to make sure that our rocket systems can get there quickly, efficiently as well. Make sure that we know how to reserve our fuel when we get to the moon. Make sure we got our geometry right. We got to fly in nice and close, take a bunch of pictures, take as much data as we can, and then swing back to Earth and make sure we can get everybody back to Earth safe and sound as well. And so that's our main challenge for Artemis 2. Now for Artemis 3, this is where it's going to get tricky too. So we get to the moon. We already know the roads due to Artemis 2, and then we're going to go to the South Pole of the moon. So the geometry is going to be slightly different just to get to that bottom part of the moon there and then land safely. And the South Pole of the moon has its own interesting challenges. Definitely some interesting geometry going on here with Artemis 3, but some exciting operations there nonetheless. So why go to the South Pole of the moon is because there's just some really weird stuff going on in the South Pole of the moon. So the big thing here is just looking at just this is going over several hours to several days worth on the moon here. Look at the shadows moving across just the South Pole portion of the moon, though. There's some places here that take the phrase where the sun don't shine to a literal sense. And so in these deep, dark craters that you see here, there's some weird chemistry going on. There's potentially some weird geology going on. There's some weird radiation going on. All this different dark areas not only has some weird dust, the dust really loves sunlight, but it also hates the dark too. So whenever there's areas here that has any bit of light, lunar dust will actually slowly creep up and create a little haze, just a little dusty haze, and then it'll settle back down because it doesn't like the night. And then the chemistry, what is condensed, what kind of ice is at the bottom of all of these different craters? And that's most of my job here at NASA, is to figure out what kind of ice are we dealing with, how cold do these deep dark craters can actually get, and then why do we even want to bother the ice in the first place? So let's journey on through that, shall we? We call these PSRs, permanently shadowed regions. So permanently meaning truly Sunlight does not reach those areas. It could be deep craters, or it can be the side of a crater, just somewhere where there's just like no sunlight. And because of that, it can get extremely cold. And this is the neat part, is that it can get as cold as Pluto at some of these places on the moon. So we're talking negative 400 some degrees Fahrenheit. Very, very cold. It's freezing cold there. And it can have seasonal temperatures too. So there's some of these craters that can get just a tiny bit warmer. And by tiny bit, we're going from negative 400 degrees Fahrenheit to about negative 350 degrees Fahrenheit. So from cold to just nippy in that case. But how old is some of this ice? Some of this ice might be practically a billion plus years old, which is fascinating. But how did it get there? How spread out is this? How deep is it? We still don't know. We only know just very little about like where this ice potentially is. So this is a bigger map of the south pole of the moon. So all the orange outlines that you see here are where we potentially think is some of the darker areas where there's no sunlight, that there is more likely ice at these places, and it's scattered all over the place. These are the larger areas, but we also realize that there might be little itty bitty pockets of ice everywhere, everywhere on the South Pole of the moon, which is great. So if we were to look at a temperature map of the moon, I wish the moon was this pretty and this rainbow colored. By all means, that would make my job really fun. But nope, this is a thermal map. So a temperature map of the moon. So the blues and purples that you see here are the really, really cold temperatures. The reds and the yellows and the greens, really hot temperatures. Not hot in the sense of like, oh, it's summer on the moon. No, nothing like that. But just warm enough that there's not going to be ice in those areas. So we're looking at the purple and blue areas though. But why I'm showing a temperature map is because we're not just looking at water ice on the moon. Isn't that cool? There's more than one type of ice on the moon. So if we were to look at what can freeze at different temperatures, so at in this case, the slightly warmer temperatures there, sulfur and sodium can freeze at very high temperatures, going all the way down to about 120 some Fahrenheit. Now we're looking at water and methanol freezing and condensing at low temperatures. Now let's look at really, really cold temperatures: carbon dioxide, ammonia, sulfur dioxide, which is a very fascinating ice and a very dangerous ice too. Hydrogen sulfide and sulfur dioxide, very, very challenging ices, probably in itty bitty amounts, which is safe, but it's still very dangerous ice. It's dangerous in the sense that you do not want to breathe it in, you don't want to drink it, none of that. So, water is probably your safest ice out of all of this. So the challenge, we want to sample these. We want to be able to go to these dark areas and take a little itty bitty probe, a little itty bitty drill, maybe a little shovel, scoop some up and bring it back home. We want to sample these. The issue is that the temperatures can really affect how you sample it. So tools can get hot. If you were to bring a rover to some of this ice, the rover itself is going to emit heat as well. You don't want to just laser the ice either. That can melt the ice. That would be bad. And then dust, if you're just walking around and kicking up dust and everything, dust could unfortunately cause your ice to also like melt, and a term that's called sublimate, where a solid immediately forms into a gas. So that is sublimation there. So that would not be so good too, to do that. So how do we collect it? How do we sample it? What kind of testing can we do with this ice? All of this is still being discussed right now at different NASA centers and different engineers. So that's mostly with Artemis, and then as our lovely introduction had, is that I'm part of EHP, the Extravehicular and Human Activity Program. So I help manage astronauts. I help manage what astronauts should and should not do at the surface of the moon. And so a lot of that is a lot of paperwork. There's a lot of policy writing and everything, but we have to make sure we document everything. Everything can be a risk, so that's the main issue right now, is what kind of risks can our will our astronauts potentially have at the surface of the moon? And this includes rovers, it includes landers. What kind of tools will they use to make sure that they're careful with it, and they don't just toss a hammer off to the side and break something. No. There are suits, there are suit risks. So what happens if a suit leaks? How do we fix that? How do we make sure that what we leave on the moon is sealed tightly, or it's not going to just rust away on the moon either? I make sure that what we do on the moon is very contained, it's very safe. It doesn't cause any issues, and vice versa. The surface, we're dealing with temperature differences, radiation is an issue, solar wind, solar storms are an issue. Everything can be an issue on the surface of the moon. The biggest issue we have is dust. Dust on the moon. You're just walking about willy-nilly on the moon like an astronaut. You're kicking up dust all over the place. That dust is gonna hang out a little bit. It's got to settle down somewhere. Hopefully, it'll settle back down on the surface, but not always. It can sometimes settle onto your solar cells. That's going to be bad because that's going to decrease your power. It can cover wires, in which case that's a tripping hazard. What happens if you have dust on your tools and on your suit and you're wanting to go back inside? You can't just do this, because that dust likes to cling, likes to static cling to you. It's really, really tiny dust. So how do we make sure that the astronauts shake themselves off before they go back to, whether it's the ISS, it could be some sort of other orbiter in the future as well. Make sure that they're as clean as possible. Make sure that their tools are wiped off as much as possible. Dust is our biggest challenge, and they're yeah. So that's going to be a fun trial and error, to be sure, with that. So again, this all goes back to what's human versus natural hazards here. So natural, like I said, is dust, the radiation of the environment, shadows, shadow effects. Shadows can mess with like, your vision and where certain things are during the day and night, and temperature. Whereas what we call induced, or rather human-based hazards, so any kind of activity, astronaut activity, tools, the power, the batteries, any kind of leakage, that would be really bad if we had any kind of battery leaks, but we got to prepare for everything. So every little thing, every little activity, or every little piece of battery that we put on the moon, we need to make sure that we're like, okay, what's our plan B? What do we do to fix this? What do we make sure it doesn't get any worse either? So there's a lot to do. So, all essence, why bring samples back? We want to know, where did this ice come from? How does it form? Now that I told you that there's more than one type of ice, how did it all get to that part of the moon? Why isn't it just everywhere? But also, that chemistry needs to come from somewhere. Whether it came from the volcanoes of the moon. Yes, the moon actually did have volcanoes. Did it come from the inside and it just kind of burped out of the moon and then over to the poles? Like, how did that may have happened? Did some of this come from the early baby moon when it first formed, or did it form later? Maybe a giant impact happened on the moon, which happened several times. Maybe it excavated something. Where did this come from? And then learning about the different sampling techniques too. Does a shovel versus a drill? What's the pros and cons, right? Which one worked better, or which one was like, okay, maybe they both didn't work. Then how do we fix that? How do we make sure what we're sampling is good enough? How do we improve upon it? And then what can this ice on the moon tell us about all the other ice all over the solar system? There's water ice everywhere in the solar system, but they all do different stuff on different planets and moons, which is really neat. So just learning about the ice on our nearest neighbor of the moon is truly fascinating in there. So with Artemis, there's still lots to do. There's still lots of challenges. And with that, I'm happy to dive right into question mode.
All right, I'm back. Hi, everybody. Thank you so much, Caitlin. That was amazing, very interesting and exciting. And so we are going to open the floor up for questions, and are open to lots of different questions. Try to keep them related to the Artemis mission, space travel, science, what it's like to work for NASA, what it's like to be a scientist. Maybe Caitlin can tell us about how she was inspired to become a scientist. So I will let you guys ask a few questions. I might have a few of my own to fill it in. And we will start with some of the hands that are raised here. And so I'll go ahead and call on Ayla. Hopefully I'm saying that right with your hand raised. You're top on my screen. So Ayla, if you can, yeah, go ahead and unmute yourself and ask your question.
Can you hear me?
Yeah, I can hear you.
Okay, it's Alea.
Sorry.
I have two questions. These are at the top of my list. I have a whole list now. But one is, do you think that Mars or the moon will be more habitable for us to go on first?
Ooh, that's an excellent question. The easy answer would be the moon because it's closer.
Okay.
And there's not as much hazards as Mars. Mars is certainly bigger. It has probably a little bit more interesting minerals, in my opinion. But the issue with Mars is that it has global dust storms. And so dust is already an issue on the moon.
Yeah.
Let's just times 100 that on Mars. Um, so it just gets way worse. Or you know what? I shouldn't say worse. Or just say hard mode
Okay.
on Mars. So if anything, the goal is for both, but we need a better understanding of how do we do this on the moon first and kind
Mhm.
of get a sense of like, okay, how do we deal with dust on the moon? And then ramp it up, and then we can get ready for Mars and go like, okay, we've tried this
Yeah.
on the moon, now we can go to Mars. So habitation, it would be easier to do it on the moon because it's closer. We can send resources um up and back quickly as well.
Yeah,
It'd be like
faster.
a quick weekend trip as opposed to a one-way 9 month, you hope that you get your granola bars there in time kind of situation. So I'll vote for moon, but the goal is for both eventually. Maybe not in my lifetime, hopefully in yours.
Yeah. My second question would be, sorry, if, like, I know you guys are trying to get ice back from the moon to Earth,
Mhm.
wouldn't the ice melt, and would it, like, have any impact on, like, the humans' system, like if we touch it or anything like that?
That's an excellent question. So that's still something that we NASA are relaying to the whole planetary community right now. The lunar
Okay.
planetary community is kind of joining forces right now and figuring out how do we contain it?
Mhm.
How do we make sure it stays cold? Because that's very important. As soon as it melts, your science is gone.
Yeah.
Unfortunately, you want to keep it as solid as possible. So it's essentially like picking up a popsicle and then putting it in a container of some sort, keeping it cold, and then traveling to another planet and then through a burning atmosphere to land,
Mhm.
and then to transport it into a laboratory and then pop that sucker open and then do some tests. So it sounds easy, right? Yeah.
Not
So
really.
yeah, not really at all. So currently right now, the current discussions right now is we have a pretty good idea of how cold it needs to stay, but what should the container look like? How much ice can we sample on the first go around? It's going to be tiny. I can guarantee
Mhm.
it's going to be like
Yeah, because
barely
you
the
have to
size.
check the temperature and all that. Yeah.
Right. It also, this will be the first time we do this. So, tiny sample just to say like, yeah, we did it. Yay.
Mhm.
What went wrong? Maybe.
Yeah.
But then make sure that your container isn't going to heat up either. So we want to make
Yeah.
sure some sort of metal that is going to keep cold, that it's not going to rust apart either. There will be some slight uh gas uh containment out of the ice, unfortunately.
Mhm.
That can't be
Do you
helped.
think it will be, like, way too cold, like, negative beyond negative? Like, we won't have a container to, like, hold it type thing?
So thankfully we do have laboratories out there, and I myself have worked at a laboratory that can get as cold as Pluto. So there are
Mhm.
metals out there that can
Hold
withstand
that temperature.
very, very
Yeah.
cold temperatures. And so what's cool is that there's a whole level of physicists out there that do quantum mechanics in a laboratory. They even have to go colder than Pluto. So we're learning from those guys. We're learning from those scientists and go like, what kind of metal, what kind of laboratory do you work with that can get colder than Pluto? And then can we talk, can we borrow
Mhm.
some of that? And so that again, just right now it's all about chatting. It's all about like, well, what about this? Can we test this? And everything like that. So right now it's all talking and testing, and
Okay.
it has to happen very fast right now because Artemis 2 is truly around the corner and Artemis 3 is uh may seem like several years away, but for
Mhm.
us that's very,
It's
very
right.
soon.
Okay.
Yeah.
All right. So
Thank
we're
you.
gonna go ahead. Thank you. We'll take one more question. I'm gonna throw it to one that's in the chat because it's related to what you just asked or said about Artemis 3. So Lamar in the chat asked, what are NASA's plans after Artemis 3? Is the mission complete?
Nope. So that's the fun part about Artemis, is that we want to model it kind of after Apollo, where Apollo was very regular and they're like, okay, this is what we're going to do for Apollo 11, 12, 14, 15, 16, 17. Each one was almost a template of the previous one, but they all did different things. They all visited different sites. They all had different tools and instruments. And so we want to do that again. We want to go like, okay, the South Pole is pretty big too. We can send them in different areas, give them different tools, test out different stuff. Later on, we're going to give them a giant rover to play with too. That's going to be fun. We're already in the process of designing that. It's going to be great. It's called the Lunar Terrain Vehicle. So all of this exciting stuff. What do we do with astronauts and rovers working together simultaneously, as well? Because rovers can do certain things that astronauts can't, but vice versa. Astronauts can go to certain places, and big rovers aren't able to maybe go down into a crater, or they'll tumble. So all of this stuff is exciting. We're already thinking all the way up to Artemis 7 and beyond. So it's going to be a bunch of Artemis missions, one right after the other. But not to say that we don't know what the purpose of or the exploration of Artemis 4 is going to be as opposed to Artemis 6. All that is still, we don't know yet, because we still want to know what 2 and 3 are going to do. What are 2 and 3 going to tell us? And then we learn. It's called lessons learned. Because we know we're going to make mistakes. That's the fun part about science. We're going to make mistakes, So we learn from it. We go like, okay, that didn't work. Or, oh, you know what? Maybe we should have done a tighter turn here. We could have reserved more fuel going this way. Let's write that down. Let's do it again for 3. Okay. Oh, whoops, you know what? We accidentally broke a tool on Artemis 3 or something. How do we fix that? More duct tape. So all of these are lessons learned, and by all means, that's exactly what you guys are going to be accomplishing during your challenges during Artemis Roads too. Is that there's going to be things that may not work or break down, and so in your mind, it's like, what worked? What can we improve upon that? And you test it again, and that's essentially what we're doing with Artemis.
Nice. That's exactly right. I hope they do learn that, right? Nothing ever really works perfectly the first time. You got to test it. Okay,
Yep.
we're going to go back to the video here. SM Ruthie, I'm not sure what your name is, but if you're still there, you got your hand up, go ahead and unmute and ask your question.
Okay, it's Sama, it's just the wrong name.
Okay.
But my question is, would we have to terraform or like change the moon to build houses or like habitats on it?
So thankfully, no. So what's great is that the moon is fine just the way it is. The only thing we need to be careful of is just the environment. It's dusty. There's going to be radiation. Not so good with that. And by radiation, I mean way worse than a sunburn here. So we got to be very careful of the environment. So what we do with that is 2 different things. One, how do you build a sort of rocky igloo type habitat? So whether it is made out of rock or it could be made out of maybe a certain kind of cement, it could be made out of maybe a special kind of plastic. But there's got to be some sort of material that can withstand and keep something safe from that radiation, and make these kind of, probably dome like structures. And the other thing too is, can we make underground tunnel systems that will be safe for astronauts as well? So that is something that certain geologists around the world are doing right now, is they are looking at different cave systems all across the globe, to figure out like, okay, can astronauts be in caves and lava tubes and not only do science but also be protected and safe? So there's 2 different ways about that. Is we're either on the surface or maybe we'll be like underground and be mole people, astronaut mole people. There you go. So that would be fun. But so it's still like, how do we make sure that we're safe is the main part. But no, we're not going to terraform the moon, which is great. That's fine. That's really, really difficult to do. So we're going to keep it easy on ourselves.
So, I just want to know, if it's really cold, wouldn't that ice kind of be buried under like frozen soil?
Exactly. Excellent. Excellent observation there. So there might be a little bit of it, at least on the surface, because it would have accumulated and kind of crystallized up onto the surface. But some of that can get pushed down way over time. So we're talking billions of years over time. The issue is that we don't know how deep it is. And also, we don't know actually how solid this ice is. I say ice, so you could think of an ice cube, but in reality, it could be a little itty bitty ice grains all over the place, in which case, what we would call as fluffy ice, which is really cute to say, fluffy ice. If it's fluffy ice versus solid, rock solid ice, we don't know. We don't know that yet. So that could be an issue. But that's the fun part. That's why we want to sample it too. How deep does this stuff go? How cold is it? What type of ice? Where did it come from? All that we still need to do. But yeah, it would certainly be buried. We just don't know how deep.
Great. I love the idea of fluffy ice. I'm gonna be Googling that later, probably to look up pictures of what that might look
Oh, yeah.
like.
Porous fluffy ice.
Nice. Okay, let's do one more video one and then we'll stick to one in the chat. So how about Aaliyah? Why don't you go ahead unmute and ask your question.
I have two questions. First is, why did Apollo 11 start at 11?
Excellent question. Yeah. So before Apollo, we had the Mercury and Gemini projects where we would blast off humans and then they would do a few orbits around the Earth and then come back down safely. And so with that, it helped with the numbering leading up to Apollo. We did try to have at least an Apollo 1, didn't work out very well, unfortunately. And so we just kept running tests and tests and tests. And finally, by the time it got to version 11, then it was just like, okay, now we can finally have boots on the ground. So we did have Apollo 8 and it spun around the moon. So Apollo 8 and Artemis 2 are almost identical with swinging around the moon and come back to Earth. So it just helped with the numbering system. And then 11 was like, boots on the ground. Hooray, we made it.
Awesome.
Right.
That's a great question. Okay, that was Leo, right?
Yeah. And
Okay,
then
hi
I
Leo. You have one more?
Yeah.
why would we want to go to the moon in the first place?
Oh, that's a great question.
That is a great question. Yes. So all sorts of answers with this too, and they all depend upon who you ask, because we all come from different science backgrounds. So for me as a geologist, it's like, oh, there's ice on the moon. Wouldn't it be cool to like go figure out what's all that about? Why we're sending rovers to other parts of the moon too. We want to know more about lunar soil and maybe like eventually planting on the lunar soil. But we need to know, what is that soil made out of and is it plantable? And then there's volcanoes on the moon. How did those form? What kind of material is that? What does moon lava even do? Which is cool to think about, that there's moon lava. So how did that form? You know, was it sticky at one point, or what was it, runny? How did it form mountains on the moon? So as a geologist, that would be that reason. For people who maybe study radiation, with astronaut safety, so there's that version there. For people who study dust, why would the dust loft itself into a haze? The Apollo astronauts actually witnessed this, and they wrote it down in their journals that during the daytime, the bits of dust would float and create a haze layer, and then it would settle back down. So what's going on there? And dust being static, clingy to everything. Why? What's the physics behind that? So people who study dust would want to know that as well. Also, just the origins of the moon. So people who study the innards of the moon. How did it form? Something that so massive smacked into baby Earth billions of years ago, and then out plopped a baby moon, and then spun around, and then how did all that form? What are the origins of the moon back then to now? So all of these different answers, it really does depend upon what we study, and all these different mysteries. Most of its origin, but some of it's just like, oh, the moon is very active in its own sense, radiation, dust, um, the geology and everything. So it's a matter of like, well, why not? It's close, it's closer, so it's in that case, it's cheaper to get there. But the moon also affects a lot of stuff here on Earth as well. So we use moon phases a lot by seasons, and certainly for photography, but also in a cultural sense too, is that we use the moon for also nighttime as well. A lot of nightlife relies on the moon as well. We also have tides by the moon as well. So understanding that relationship with like the moon and Earth is also a big understanding of that as well. So
Okay.
that's a very long answer, but like there's a lot of stuff to do.
There's a
on
lot
the
of good
moon.
reasons. That's right. Okay, we're gonna go back to the video. Thank you, Leo. And we'll go to the person that's topped on my list here, which is Aaliyah. Why don't you go ahead and unmute yourself and ask your question? Looks like you're unmuted, but we can't hear you. All right, we'll give you one more second. If you can't, if your speaker isn't working, you can always put your question in the chat too, and I'll ask it. Okay, we're gonna skip down. How about Matthew O? Why don't you go ahead and unmute yourself and ask your question?
Yeah, so my question is that let's say we use a drill. Wouldn't the dust just go onto the ice? Sure, there's no atmosphere or whatever, but because we're doing it so close to the ice itself, wouldn't the dust just go on top of it?
Yep, pretty much. So that's what we're hoping doesn't happen a lot. A little bit of dust maybe won't be so bad. So this is something that we need to figure out still, and this is why Viper is going to tell us maybe some answers. So Viper is a fabulous rover. It's about the size of a golf cart. It's a heavy one too. It's nearly 1,000 pounds. I believe it's 990 pounds of a rover. So it's small but mighty. But it's going to have a drill on it called the Trident drill. And so this drill is going to drill into soil and ice as deep as it can, and give us a lot of the chemistry of what's going on there in with other instruments. But that drill is going to be the first of its kind. It's going to take a bunch of pictures to make sure, like, did it work? Did it not? Lessons learned again, because it's the first time we're doing this with a drill, especially with ice. So all of that is still to be determined, which is really cool. Is that Viper should help us out with that, and that way that can tell us like, okay, what do we need to improve with our own drills or cores and other instruments as well.
So my second and final question is how big would the rocket ship need to be, or what are you planning how big the rocket ship would be because of the ice? Like, it may just be little or maybe tons of ice. How big is the rocket ship planned to be?
Hopefully the rocket doesn't need to be too big, because the larger you are, the more fuel and that could get that could get tricky. There are plans to have really big rockets. For the first few samples, we're talking tiny samples, just itty bitty little samples of ice. I mean, best case scenario is like this much ice, like really tiny bits. The issue that we have though is that we don't want to just collect ice, but also rocks as well, and rocks can add weight. So it's not so much of how big of a sample can we get to bring back home, yippee. It's more of a, oh, we can't just pile up all the rocks onto the rocket and bring it back home. We have to be very careful of not to overweight everything. And our like little storage boxes that we're going to put all the rocks in and everything can only hold so much too, or it's going to break. So we have to be, again, just very careful. We have scales to make sure like, oh, you know what, we've hit our limit of this many kilograms. That's it. That's all we can collect. Let's go back home. Like, you better hope that you picked a good rock to bring back home, because there's a lot of pretty rocks out there. So
You guys love
and
rocks.
soil.
You love geology. Geologists all
soil,
have a
too.
box of rocks under their desk.
Hey,
Thank
I
you.
mean, I here's my desk rock right here. I mean, I have a lot of desk rocks. I have like
Yeah.
another rock here.
You might be a geologist if
Rock
you have
here.
rocks on your desk.
Here's a polished rock.
That's
So
pretty cool.
great.
I love it. Show and tell.
Show and
Okay.
tell. Got my
I
rock.
see Aaliyah's question. She didn't get her microphone working, but it's in the chat. she says, my project advisor mentioned as we work on mission objective 4 that we're going to be trying to build a sustainable living habitat on the moon. Could the permanently shadowed regions affect plant growth and temporary living? That's the first question. Then she's got a follow-up one. So do you think the permanently shadowed regions are going to affect the astronauts' ability to grow plants?
Probably, because it's gonna be really, really cold for any sort of plant life to there's gonna be no sunlight there. However, if there's a way to draw out the hydrogen and oxygen that make water, if you can somehow draw out that hydrogen and oxygen, just kind of slurp it out of the soil there, there's your water to water your plants. And so if you kind of draw all that little hydrogen and oxygen out of the dirt, and then you got your water, and then you just put it somewhere where there's sunlight, so not in a dark shadow, but somewhere where there's light for several hours to days on end, then there you go. You got your sunlight and got your water. Now, does the soil itself need certain nutrients? More likely. And so that's something to also look into as well, is maybe how, is there some way, I'm just asking you guys now, is there maybe some way to do like a little itty bitty greenhouse, a little biodome for these plants? And that's something to maybe look into as well.
Yeah.
But otherwise it might be a bit cold in the shadows there.
Exactly. Yeah. Well, that's something hopefully the students will be thinking about, is how can we enrich that soil? And so I'll ask Aaliyah a second question, and then I'm going to follow it up with some pre-submitted questions and other ones in the chat because it's kind of related. So another thing that the students are trying to do is build a habitat. So her second question was, do you think clay would work for the building? So just generally, maybe what kind of things would you build a habitat out of on the moon?
That's an excellent question. So there are possibilities. There are laboratories. There's a laboratory, I believe, in Florida that I'm thinking of, and another one in Texas that are looking into 3D printing bricks and other housing, like giant Lego bricks, but 3D printing with fake lunar dirt and cements and clays, and figuring out, can we not only 3D print something that is rocky, but can it hold up as well? Not only just hold up in it's not going to rain on the moon, thankfully, so it's not like it's going to melt away. But make sure that we're not accidentally suffocating our astronauts. That would be bad. But also make sure that it's a radiation blocker somehow as well. And so there are specific minerals and metals that can help shield those astronauts as well. So whether the clay and moon dirt can make like an outer shell and maybe an inner shell of metal to help with the radiation too, without creating a human microwave. So all of this is still being tested right now, which is exciting because again, we don't really understand the materials that well. So that's the fun part. And 3D printing is just so cool to think about, of just, can we 3D print moon bricks?
Yeah, I love that. Okay, so my follow-up questions, some of them are from, like I said, pre-submitted, and some of them are in the chat. So I think this one was from Leisha in the chat, and her question was, what is moon dust made of? What makes it dangerous? And then I'm going to follow it up from a pre-submitted question from Iris. So it'll be 3. This is an easy one though. Have you ever touched lunar regolith?
Okay, so so that first question of
What is it made of?
like, what is it made out of? So dust, because I mean, this stuff is tiny, very, very tiny. It's very shiny too. It sparkles a little bit, but it's very, very tiny. Most of it is like silica, and so like quartz, aluminum, nickel, iron, magnesium. So you got bits of metal in there as well. You got some, aluminum may not seem so bad. Silica doesn't seem so bad. The issue with all of those combined into itty bitty little pieces is because it's all glassy. It's all shards. It's all sharp in the tiniest little sense. But because it's sharp, they're all have like little barbs on them. And why that's dangerous is because it'll stick to everything. So you can't just do that because it'll just stay there. It'll just stick to you because all those little itty bitty barbs. If we were to like I see a big moon dust grain and blow it up and see it big, you'll have all these little sharp barbs everywhere. All that can stick into the fabric of your spacesuit, which is bad. But also, if you were to just breathe that stuff in, all those little barbs will get stuck in your lungs. That's not good. No bueno. So this is a big reason why this is dangerous. Another reason too is that it's static. So if anybody has had a balloon, they rub it in their hair and you get all that kind of static electricity and everything. So that static can also help with that dust being, it creates a haze and everything. It will stick to your solar panels. It'll stick to the rover wheels. It'll stick to the suits. It'll stick to the tools. It'll stick on everything. So it's inevitable. There's no way to really terribly make it go away entirely, but we need to design better brushes. I believe it was Apollo 15. We did bring a brush, just a regular brush from Earth, and we tried that on the spacesuit. Didn't work. Absolutely did not do anything. So we learned make better brushes for future astronauts. But yeah, that stuff is very glassy, very sharp. Do not want to breathe that in.
That's a great question. Okay.
Yeah, and then the second
Oh,
question.
sorry. Yes.
Yeah,
There
there
was
was
a second. No. Have you ever
Here-
touched it?
Have I ever touched it?
Yes.
So I have touched moon rocks before, but like bigger solid pieces of moon rocks. I have touched those before and looked at them through microscopes and everything, and they're really pretty. Really, really pretty through a microscope. But moon dirt, no, I have not. I would need like gloves and need to be like behind glass and everything, and just to like poke it. It's like no, I don't have moon dirt on hand. Unfortunately, it'd be really fun, but no, very dangerous though. I just said dangerous.
That's right. The stuff that we sent you guys, by the way, is an educational version of it. So it's not, you want to breathe in a lot of it, but it's not super bad. Okay, so we're gonna go top of the video list here to Karsten. I'm probably saying your name a little bit wrong. Karsten, do you want to go ahead and unmute yourself, introduce yourself, and ask your question?
Thank you. And also, you got my name right. You're one of the few people who gets it right the first time.
Okay, great.
My question is, what is rocket fuel made of, and is it expensive or hard to make?
Ooh, good question. So the bigger fuel chemicals to get us out of the atmosphere, loft us up into space, that stuff is very chemically dangerous. Very chemically fun to mix. So hydrazine is the big word component there. So very, very big, nasty chemicals. But it gives us enough of a boost to get up there. Now, once we are on the moon and say if we need some sort of fuel supply, most of that is actually just going to be your oxygen and your hydrogen and a little bit of carbon. And that's all you really need is just to mix those up. So guess what? With the water, there's your hydrogen and oxygen.
Interesting.
And the carbon you could get from the rocks, you could get from methane, which is carbon and hydrogen as well. So hey, guess what? Double the hydrogen there. So all of just those different kinds of very simple chemical compounds on the moon, we would need to somehow split apart typically by a chemical process called pyrolysis, pyro meaning fire. So you essentially burn your chemicals to separate. So, boop, there's hydrogen, there's your oxygen, there's your carbon, and then you reassemble them by different chemical means as well. And then you can essentially make a very DIY, very basic level of fuel on the moon. Maybe not as big of a thrust as you need, but at least enough to maybe rove around, and you don't really need that big of a lift to get back to Earth either. Worst comes to worst.
Yeah. Great question. Okay, I'm gonna go to the next video one. Ellie, I saw you had one in the chat, but you also go ahead and unmute yourself and ask your question.
Can you hear me?
Yeah, we can hear you.
Hi, I don't know if it's related or not, but I was just wondering if we want to learn more about this and do something related in the future, like work for or with NASA. Do you have much to say on that?
Ooh, yes. So not only is the moon very busy for us right now, though, but essentially there's still so much to do every which way that you look at it. Like, we haven't really explored much of the outer solar system. So what is it going to take to build a mission to get all the way out at Uranus and Neptune? We've gone to Pluto. What if we want to sample something from Pluto? What's that going to look like in the future? Jupiter is this giant planet that, fun fact, it was almost a star. So why didn't it become a star? What happened to it? And then all the different moons around Jupiter too, they all do weird stuff. You have like the dinkiest little moon of Jupiter, and it's the most volcanically active thing in the whole solar system, and it's bizarre. Whereas you have moons that hold oceans underneath them. How do we explore the oceans of some of these moons as well? And I'm just talking solar system too here. And Mars, we want to send more rovers to Mars. We want to eventually build habitats on Mars. How do we make sure that we're safe from giant, thick, dangerous dust storms on Mars? And then asteroids. Asteroids are zipping around all over the place. And so there's something called planetary defense as well. So how do we make sure that we, people of Earth, are protected, and make sure, like, okay, there's going to be an asteroid zipping very, very close. What are we going to do about that? So there's that part of NASA as well. We want to build giant telescopes. So the James Webb Space Telescope is giving us all of these fantastic, beautiful images of galaxies and nebulae and clusters and everything. And they actually, most of them work on the floor above me here. Most of my floor are space geology people, so we all hang out and talk about rocks. The floor below me is more of the radiation folks, the magnetospheres, the people who study storm systems on other planets. Isn't that cool? There's lightning storms on Saturn. Isn't that neat? But how does that work? So all of these different things are still open. It's not like we have a definite answer to any one of these things at NASA, or even at any university that collaborates with NASA too. And so all of these different questions are still going about, where there's never going to be like, oh, well, we solved that, next. No, there's always someone working on something. And like myself, I work on the moon most of the time, but I also have a few students working on Pluto. I have a student working on Mars right now. I myself am doing some asteroid work on the side. So we're kind of just everywhere and having fun because there's always something to do.
Great answer. Okay, we're gonna keep going down the list a little bit, just so you guys know and I will, and probably in about 5-10 minutes, I'll see how we're doing, because we are at 4:30. I love having lots of questions. This is a great problem to have. I just want to apologize in advance if we don't get to every question, but we'll get to as many as we can. If you're okay answering a few more, Caitlin.
Absolutely, absolutely.
Perfect.
And so for any teachers and educators out there listening, if your classroom has more questions, feel free to reach out to Darcy for my contact info, and happy to answer questions to specific groups out there as well. So happy to do that in the future.
Thank you. I appreciate it. Okay, Jen Larson, why don't you go ahead and unmute yourself and ask a question, or have your student ask a question?
I have 3 students that are going to ask questions. So.
Okay.
All right, let's do this.
Okay, so my question is, how will the machines work while getting oxygen out of the ice?
Oh, good question. We're still working on that. Mainly because do we do it as a drill? So hopefully Viper can tell us whether a drill is going to work or not. Or do we use a straw and suck it up? Probably not the best way to do that. But we haven't tested it, so we can't say no entirely until we test it. And then do we take a bunch of dirt and do something with it to take the oxygen out bit by bit? So all of these different things still need to be tested. So a good thing is that we have fake lunar dirt, which I believe Darcy said that some of you are already playing with, which is great. That's what we use. That's what most of us use, whether at NASA or at different universities too, is that we use fake moon dirt to help with that kind of testing as well. So good question. Right now is there's still a lot of tests to do. So we don't have one single answer yet. And it might be several different answers.
Okay. So it also another question is, if dust were to get into like the habitat on the moon, would it damage the habitat?
So it's probably going to be okay for the most part, as long as there's some way to monitor, make sure that there's not huge piles of dirt everywhere. We want to make sure that maybe there's some sort of cleaning, maybe every third day that they're in the habitat. You do a nice sweep of dirt. The major issue that's going to happen is that because the dirt is sticky and it's staticky, it's going to cling to everything. It's the major issue with this is that it's going to cling to the door. And so if the door isn't able to latch properly because it's lined with moon dust and it's not going to seal properly, that's not going to be good for our astronauts, nor their breathing air. So yeah, so airlocks would probably be the very big thing to monitor between a habitat and like a airlock system. We want to make sure that both airlocks don't get too dusty or they're not going to be able to shut, and that's not good. So that would probably be the big yikes.
Okay, so here's our third question. Will, like, if you, as you said, the moon dust like is made of metal and it has like small barbs, and since saying the moon is very cold, will it also produce some issues if it's cold and hurting you at the same time from the barbs?
Yep, it's not good either way. Thankfully with the temperature part is that we don't expect our astronauts to just stand there for hours on end either. It's going to be hopefully a very quick get some ice, get out. So we're not expecting our astronauts to stand in the cold for hours on end to do their science. And this is where rovers are going to come in handy, though, is that the rovers can hopefully withstand that kind of temperature for much longer periods, collect whatever ice and dirt that we need, and bring it back to the astronaut, and then do its testing on the moon, or to bring samples back. So this is where rovers are going to come in really handy.
Okay, thank you.
Thank you guys. Okay, we'll keep going on the video chat since you guys have been really patient. Teresa Whistler, do you want to unmute yourself and ask
Hello.
the question? Hi.
Right.
Hi from Red Lodge, Montana. We have a question about your rovers.
Mhm.
What are the rovers going to be powered by? Would it be gas or, oil or any other substance you find on the moon?
That's a fantastic question. It's going to be an interesting combination of solar panels, so solar powered rovers, which are good, and batteries. So batteries are not only going to be from the solar panels. We're hoping not as big of batteries as the Mars rovers, but that might be a future thing. Why I'm being cautious about that is because the batteries on the Mars rovers, which are the size of minivans, very, very big rovers, those are radioactive. So we don't want radioactive batteries to be near our astronauts. So we can have smaller batteries for smaller rovers. They're still going to be drivable, but they're not going to be big honking tanks yet. Maybe that's a design for later on. So we're going to test a lot of different kinds of batteries with the Artemis, the early Artemis missions coming up. What works and what doesn't, because solar panels, we know a lot about solar panels. We've done a lot for the early Mars rovers as well. Spirit and Opportunity, for example, much smaller rovers, they were solar powered. However, what happened to Spirit and Opportunity is that their solar panels were like, oh, there's the sun, yay, and then they got buried with sand over and over and over. All that dust, all that Mars dust kind of accumulated on the solar panels, and they're like, oh no more sun. I guess I'll power down now. and then no more rover. So we've learned, like, okay, we're gonna need battery sources to help out with this. There's gonna be a lot of low light or sometimes no light at all at the south pole of the moon too. So you can't always just rely on solar panels because there could be no light. There could be no sunlight to help you out. So different kinds of batteries. Now we just need to make sure that the batteries can power correctly, they can recharge, but also they make sure that they're not going to get too hot either. And also make sure that they're not going to leak, which would be really bad too. So back to that hazards list again of like, well, batteries are good, but leaking is bad.
Someone said in the chat, I like this comment to pay respect to Opportunity and Spirit. Yes. Me too. They did a great job. They outlasted their mission by many, many years.
They did. It just took on too many global dust storms.
Yeah.
For the little rovers to handle. But you know what? They did their best. They gave us many, many years of science.
They sure did.
Curiosity. We learned quite a bit about the Curiosity rover too. Lessons learned on the Curiosity rover to help us with our Perseverance rover.
That's right.
As well. So the lesson learned there, don't skimp on the tires.
Oh yeah, yes. The tires, we thought about tires in the last challenge. So these guys are missing that one unless they participated in both, but it is a challenge on the moon as well. Okay, we're gonna go to the next video one. We'll go to Michelle. Michelle, why don't you unmute yourself and ask your question?
Okay, I have 4 students with a question.
Okay.
Okay, good.
So my question is, what is the exact procedure of you testing the ice that you're going to collect from the moon?
Ooh, excellent question. In one small part, I get to help with some of that procedure, which is good. So right now we're still working on that procedure though. Those kinds of discussions happened back in December. So very just 2 months ago. So what is this procedure going to look like? That's the excellent question here. We still don't know because we're still writing it. We want to make sure we're not going to miss anything back to make sure that the ice is going to remain cold as possible, bringing it back to Earth. How are we even going to sample the ice is still a big question. Is that going to be a drill? Is that going to be a shovel? Is it a straw? Probably not a straw, but more likely a shovel of some sort, or maybe a little itty bitty sieve or something. We just don't know yet. And so what's that procedure going to look like? What kind of containment? What are we going to stuff it in and make sure it's going to be cold? And then storage. Make sure that that container is going to be put in an ice box, a space ice box of some sort, to hurl it back to Earth through a burning atmosphere and land on Earth. What could go wrong?
It might be interesting. So like when you're making those decisions, like how do the NASA scientists and engineers get together and talk? How do they make the decisions?
Yeah, so we meet every 2 weeks on a Thursday morning, early morning, and we sit and brainstorm. It's just one giant think tank of engineers and scientists for a whole hour every 2 weeks. So we're like, okay, what's this next challenge that we need to talk through? Okay, who can we contact to test this out? Does it work? Does it not? Can we test this other thing out? Does it work? Does it not? Report back to us. Maybe this part didn't work. Okay, why didn't it work? Slap some duct tape on it, make it work again. Go run tests again. So it's a constant communication cycle of engineers, go build this for us. Okay, what temperatures do you need it to withstand? Down to negative 400 degrees Fahrenheit. Go do something. Okay. Okay, you know what? Maybe it only got to negative 300. Nope, not good enough. Okay, that's gonna melt your ice. Let's see, maybe a different kind of metal. Try this other kind of metal. Maybe it needs to be thicker because maybe it just let in too much leakage or something. So all of these different things, this is constant communication. But we can't talk every day because there will be no progress. So this is why we do it every 2 weeks, is because then it gives the engineers time to build and test and report back to us. And then we make decisions going like, oh, cool, that worked. High five, yay us, have a cookie. Now the next test. It's a constant, like, most things don't work, but we're gonna keep trying anyways.
Yeah, that's great. I love the idea of you can't meet every day or else you don't make progress.
No, there's not enough coffee in the world to get me through all those meetings.
Okay, let's go. I have a list here of the hands raised. I'm gonna do, I don't know how you feel. It's 4:45. So I'm gonna do 5 more minutes of questions. Is that okay?
Yep, absolutely.
Okay,
We can.
and like I said, and if you guys do need to head out, yeah, I see Jen in the chat. Feel free to sign
Happy
off
Valentine's
if you
Day,
feel.
everybody.
Yes. I know it's
Love-
late for you guys on the East Coast. Okay, so next on my list is Ella. So Ella, you've been waiting patiently. Do you want to unmute yourself and ask your question? You're still here?
Hi, can you hear me all right?
Yeah, we can hear you.
So while we were doing the presentation, you said that you guys would use some tools. What kind of tools would that be?
So there's 2 different sets of tools here. There's the basic tools. Most of it is survival, or just run-of-the-mill fixing things kinds of tools. So we got hammers, we got your drills, small drills like power drills, your wrenches, your screwdrivers, tiny shovels, plastic baggies as well, and lots of duct tape. Duct tape has saved us a lot on the moon. And so that's also very important too. So we consider that as a tool, is duct tape. There's a lot you can do with duct tape and Velcro as well. The other set, the advanced tools, is something that we are still developing. And this is something that NASA is helping with, but we're kind of making the decisions based on what the community wants. What does the lunar community scientists want based off of their designs, which is cool. So what we do is that we set off what's called a proposal. So we set off almost like a student challenge, but to scientists. We set out a challenge to scientists going, okay, you guys design a tool for our astronauts to use, and we will judge upon how cheap it is, how easy it is to build. Does it take that much power, or does it run on batteries? Does it, is it going to break as soon as we look at it? Hopefully not. How flimsy is it? How sturdy is it? And so we judge upon all these different instruments that are submitted to NASA, and then we choose and go like, you know what? We can only choose 5. Let's make sure that we choose the right 5. But that's only for just Artemis 3. And then we might, we could do it again and have a whole different set of advanced tools for Artemis 4 and 5 and 6 and 7 and so on. And so all of this is still exciting because it should not be just NASA taking the helm. And we want to be able to share it with all the lunar scientists, all the scientists, to be like, I want to try this idea. I want to build this instrument. I have a team to revolutionize a new drill or maybe a new shovel. Maybe they have a whole new chemistry set that they want to bring to the moon. Fantastic if you can make it cheap and make it powerful to be able to work. Fantastic. I hope you're able to bring it to the moon then. Yay. And to build it for our astronauts, make sure it's also easy for the astronauts to use as well. You don't want something overly complicated for the astronauts to use. The astronauts have to wear these big, thick gloves. You want to make sure that you're not using itty bitty buttons or toggle switches that are going to break off. That would be bad. So we want to make sure the astronauts are able to use it as well. So that's the advanced tools section. So right now, we don't know what advanced tools that they're going to use yet for Artemis 3. But the simple tools we already know through Apollo. So the hammers and the drills and the shovels and all the duct tape.
Yeah, duct tape works in space. I think. I don't know.
Yes. Oh,
Seems like they use
it's
it.
fantastic to use, and it has definitely saved us a few times, especially for Apollo 17. They ran into quite a few issues, and duct tape saved the day on that one.
Now I'm curious about that story. Okay, but I'm gonna make sure we keep going down the list.
Yeah.
Okay, just a couple more. So that was Ella. So up next is Walker. Why don't you unmute yourself and ask your question?
So earlier in the presentation, you talked about negative effects that can have, like the temperature and stuff that can have a negative effect on work. How do you plan to adapt to the weather that can negatively affect the workers? For example, the galactic cosmic rays, which can break apart the moon's surface, releasing further radiation.
Yeah, exactly. So this is where the radiation folks have to come in and go like, okay, what do we do about this? So yes, radiation is very much a part of the risk of just sending astronauts to the moon. So there's 2 ways to go about this. One is the material that they wear. Their astronaut suits are actually very thick, and there's several layers. But there's certain layers that are very helpful for radiation protection in a very, very small way. Very, very small. At least to prevent them from getting sunburned, if anything. Now, galactic rays, we're talking like high energy levels of radiation. So we limit the time that they are exposed on the surface of the moon. This is why we give them a very temporary lunar vehicle to hide in overnight, get their sleep, go back out onto the surface. So we limit the amount of time that they're even able to walk around, and it's up to, I believe right now it's up to 8 hours at best, but that's including everything. 8 hours of pure activity. So that is putting on the suit, walking outside, turning on the rover, or walking to your destination, using your tools, collecting data, walking back to your vehicle or dome, your home base, and then taking off the suit. So 8 hours may seem like a lot, but in reality, it's really not that long, thankfully. So out of safety, it's really good. So more likely it's going to be closer to 6 hours, which is still quite a bit, but we just want to limit as much radiation as possible for them. And keeping in mind that Artemis is not going to be a week-long thing either. It's only going to be very short few days, and we bring them back home.
Yeah, that's the trick, right? Learning from the early missions, and then you can apply it to the longer ones. Okay, this is going to be the last one, guys, because we have taken our speaker far past her planned extracurricular or extravehicular time here with us. So I will allow Rachna, I know she's got a couple students with her, to unmute, and the students will ask the question, and then we're going to sign off. So go ahead, Rachna. If she's here, there we go.
Hi, my students here. So I'm gonna have Damien ask his question. Thank you.
Hi, my name is Damien, and I have a question. My question is, wait, wait, what was it again? Sorry.
Okay.
Yeah, the food. Say we run out of food to eat, and we have to grow our own food. But how long will it take for the food to grow? And what will we eat in that time period when we don't have food?
Excellent question. So this is still something that we're still needing to experiment with, especially like how does food even grow on the lunar surface? We haven't done that successfully yet. Now growing food in space, we have done. It's still being done on the International Space Station. I highly encourage you to look at videos and Google about the different foods that is being done on the International Space Station. It is very fascinating on how they recycle water and all the different kinds of veggies and plants that they've been growing and eating as well. So they've been able to make pizza and tacos with all the veggies that they are growing on the space station, which is really cool. Now growing it on the lunar surface, we haven't tried that yet. We don't know yet mainly because of the temperature is very harsh, and the nutrients in the soil aren't quite there, so that's a challenge. Now, in the meantime, what do we give our astronauts to eat on the moon between sleeping and when they wake up and they're like, oh, it's not like they can get a bowl of cereal. Nope. Most of it is freeze dried, put in plastic baggies, and we give them little bits of water to rehydrate that water. So think of like a plastic baggie with dry food with like a squirt of water in it, and you shake it up and then there's your food. So it can be different kinds of meat. It can be eggs, like powdered eggs are a thing. Different kinds of freeze-dried ice cream is also another fun one. You don't need to add water for that. It just tastes good freeze-dried. I've tried it several times. Different kinds of vegetables as well. We try to keep them very, very healthy, very high in protein as well, and a lot of iron and a lot of calcium in their diet as well. So iron and calcium are affected in space really bad. So the bone structures of astronauts get affected while in space. So we want to make sure that they have plenty of iron and plenty of calcium in their diet while they're in space. So knowing what types of foods are also very important as well. Not just chocolate. Just don't give them all the chocolate, all the Easter candy. There we go.
Thank you.
Great question.
Happy Valentine's.
Happy Valentine's! Yay! Hey, so yeah, speaking of chocolate, there we go.
Yeah, right. Did anybody else have questions, Rachna, or is that?
I think, are we good?
Are you guys good?
Okay,
Okay.
thank you.
Thank you so much. I'm really sorry for the people I didn't get to. Great. It's a great problem to have too many questions. We'd rather have too many than not enough. And I'm looking at the list of ones that were pre-submitted. We got to a few of them. Some of them were kind of answered anyways. But yeah, Caitlin said if you guys want to ask additional questions, why don't you go ahead and send us an email and we'll forward some of them maybe onto her, and if she's willing to answer them, then maybe we'll share out those answers in a newsletter or something like that so everybody can,
that'd be
see.
great.
That would be fun. Ask a scientist. I just want to thank you so much, Caitlin. That was amazing. I learned a ton and I'm feeling inspired, especially as we think towards our next student challenge. I hope the students learned a lot too and are feeling inspired, and most of all, get to see how fun your life is day to day, thinking about the challenges of sending humans to the moon and also all of the other cool science that you do. So thank you so much for joining us. Thank everybody for joining us. Go ahead and sign off. Yeah, you can unmute and say thank you if you want. Have a good night, everybody.
Thank you.
Thank you.
Thank you very much.
Thank
Thank
you for
you.
bringing
It was good.
Happy Valentine's Day.
Thank you.
Can't wait to complete the challenges.
Happy Valentine's Day.
Thank you guys for your time.
Thank you.
Bye.
I